In this video, I will discuss how we use Avogadro's number to count up chemical quantities. What we need to know to start is that Avogadro's number represents the number of units of something in a mole. The unit that we're counting up actually depends on the nature of the sample. So the simplest type of thing that we might count up would be a pure element sample. Okay, so if you have a pure element sample, the units that you're counting are the individual atoms. Okay, so let me give you a good example of that. This is from a website called mindat.org. Really good website for showing chemical structures. It has a focus on minerals, but chemical compounds as well. So this is supposed to represent a small chunk of copper. It would be pure copper. We only see copper atoms here. And those would be what I'd be counting up if I had a sample of copper. A couple of different ways to visualize this too. If I show you the space filling model, it might be a little bit more accurate to think of solid copper like that. And if we had a bigger chunk, it might look like this, or even a bigger chunk might look something like this. So if I were to count up or have a mole of copper, I would have a mole of copper atoms. Okay. I think the next easiest one to understand would be a covalent compound. So covalent compounds, typically between nonmetals, shared electrons, and we call that the unit a molecule. So that would be like, for example, if I had some water, right, a sample of water, and I zoomed in, I would see my H2O molecules, and they would exist as discrete particles. So if I have a mole of water, what I have is Avogadro's number of water molecules. Another way to visualize that could be this, right? So if I zoom in on my sample, I've got H2, right, 2 hydrogens and 2 oxygens, but they all exist separate from their neighbors, right? That's the sense of what we mean by a molecule, a particle containing atoms that are linked by covalent bonds. So if I have, again, a mole of water, I have a mole of molecules. And then the one that seems to be most confusing for students is if you have an ionic compound. The unit that you're counting up is the formula unit. So you might wonder, why don't we just call them molecules like we do with covalent compounds? It has to do with the structure of ionic compounds. So if we have something like table salt, we have this array of sodium ions and chloride ions, and there's no discrete particle here, right? I can't talk about a molecule of sodium chloride because we've got this kind of vast 3D structure. I could pick out any Na and Cl and consider that a unit of table salt. We just call that a formula unit because it's the unit in the crystal structure that is shown in the formula. In the case of table salt, it's pretty simple. We've got 1 sodium, we've got 1 chloride. But that's kind of the simplest ionic compound that you could come across. If you have something more complex, like in a problem that we looked at, let's see if I can find it here, dealing with lead chromate. So lead chromate is a lead atom with a +2 charge linked up with the chromate polyatomic ion, which is a chromium and 4 oxygen carrying a -2 charge overall. This problem asks you to solve for moles, which I think most of us can do pretty easily using the molar mass of lead chromate. But then it asks how many formula units do you have, and then how many total atoms. So let me give you a visual of what we're talking about with lead chromate. So if I were to zoom in on a chunk of lead chromate, I've got my lead atom with a +2 charge. The charge isn't shown here. And then the polyatomic ion chromate is something like this, with a chromium bound to 4 oxygen atoms. So if I have a mole of lead to chromate, the formula unit that I'm counting is kind of this piece here. But again, they're all neighboring one another. So I could choose, this grouping of lead and chromate, or I could have chosen this grouping of lead and chromate. There's no distinct separate particle that I can pick out and call an individual unit. And if you scale it up even bigger, you can see that things get even more complex still. You've got these, lead ions neighboring chromates, but you really could pick any of its neighbors as the formula unit. And then if we even made it bigger or bigger, you can see that we can't pick out discrete particles. That even is probably a more accurate representation of what the 3D crystal structure looks like. And again, here's a lead, here's a chromate unit, but I can't pick out individual discrete units. One last idea then, going back to our picture here, is if I go back to the unit cell, that particular problem also asks for how many total atoms you have. So when you've counted up the formula units, again, that's a grouping of a lead and a chromate, each individual formula unit has 6 atoms total. 1, 2, 3, 4, 5, and 6. The chromate contributes 5 atoms, and then the lead in the formula unit contributes the 6th atom. So we can do one last step. Once we've converted to formula units, then the total atoms we would just multiply by 6. So hopefully that helps you understand the difference between what we are actually counting when we use Avogadro's number. For a pure element, we're counting atoms. When we're counting up covalent compounds, we're counting molecules. And when we're dealing with an ionic compound, the most accurate way to state that is that we are counting up formula units, which is literally the grouping of atoms shown in the formula. Thanks for watching.